We live in a world that feels solid, predictable, and reassuringly familiar. Tables stay put, planets follow their orbits, and cause seems to lead smoothly to effect. It is a stage where matter behaves as expected, where the laws of classical physics explain everything from falling apples to the arc of a spacecraft crossing interplanetary space. Yet beneath this everyday stage, hidden beneath the curtain of perception, lies a world so alien that it defies every instinct we have developed over millennia of survival. It is the quantum realm, a domain where certainty dissolves into probability, and matter itself dances to rules that appear paradoxical when judged by ordinary logic. Imagine shrinking far below the scale of atom, plunging into a place where particles are not billiard balls but elusive clouds of possibility. Electrons orbit no nucleus the way planets orbit stars. Instead, they smear themselves into diffuse patterns existing not in one location but in countless potential ones simultaneous. Only when we attempt to measure do they reveal a definite position, as if reality hesitates until forced to decide. This is not a poetic metaphor, but a rigorously tested principle known as wave-particle duality. Light, too, refuses to pick a single identity. It flows like a wave across vast distances, yet arrives at a detector as a discrete packet of energy. What is it truly, a particle or a wave? Quantum mechanics answers both and neither. The very question collapses under the weight of observation. Such ideas unsettle us because they strike at the foundation of how we understand causality. In our macroscopic world, events follow chains that appear orderly and deterministic. If you push a glass, it falls and shatters. Nothing ambiguous occurs in between. But at the subatomic scale, outcomes can only be predicted in terms of likelihood. An electron might be here or there. A photon might pass through one slit or another, or perhaps both simultaneously. Reality is not a straight line, but a branching of possibility, where certainty emerges only after measurement collapses the haze of probabilities into one concrete fact. To the human mind, honed on survival in forests and savannas, such ambiguity feels absurd, even irrational, and yet this strange underworld governs everything. The chemistry of stars, the mechanisms of DNA, the very stability of matter all depend on quantum laws. Without quantum tunneling, the nuclear fusion that powers the sun would never ignite. Without the exclusion principle that forbids electrons from occupying identical states, atoms would collapse into featureless lumps, erasing the diversity of elements. In short, the macroscopic reality we consider normal is built upon an invisible scaffold of rules that appear anything but normal. It is here that contrast becomes striking. Classical physics describes a universe like a precise clockwork, each gear turning predictably, each outcome determined by initial condition. Quantum mechanics, in contrast, paints a cosmos where uncertainty is fundamental, where even the act of observation changes the system observed. Instead of reassuring clarity, we confront indeterminacy. Instead of objects existing with definite properties, we encounter probabilities woven into the very fabric of existence. For centuries, scientists wrestled with this dissonance. Einstein, despite his genius, balked at the idea that God plays dice. Niels Bohr, one of quantum theory's architects, countered that the dice are not merely metaphorical, they are reality itself. This intellectual tension reflects the struggle of human intuition when faced with phenomena that resist being framed in familiar categories. Our senses evolved to track predators and fruit, not wave functions and quantum superposition. No wonder the deeper truth feels alien, and yet, alien though it may seem, the quantum world is not remote from it. Every particle in our bodies, every photon striking our eyes, every atom composing our breath obeys these strange rules. We are not just observers of this realm, we are manifestations of it. What feels solid beneath our feet is, at its core, an orchestra probability resolving into patterns we interpret as reality. The unsettling part is recognizing that solidity itself is a convenient illusion, one generated by forces and symmetries invisible to us. This recognition leads naturally to the next question. If quantum mechanics undermines our classical intuition, what does that mean for our understanding of reality as a whole? Is the universe itself deterministic, or does it weave endlessly through branching possibilities we can only glimpse? Certainty once reigned supreme. For centuries, Isaac Newton Newton's laws offered humanity a crystalline framework of order. Every object, every motion, every planetary orbit could be predicted with near perfection. The cosmos appeared as a vast celestial clock, its gears grinding with mechanical inevitability. Determinism was not simply a scientific position, it was a philosophy of life. If one knew the forces at play, one could, in principle, calculate the future of every star, every drop of rain, every human gesture. The universe felt conquered, tamed by equations that promised certainty. Yet beneath this majestic order, unease slowly gathered. The late 19th century bore witness to stubborn anomalies that Newton's perfect mechanism could not explain. Blackbody radiation, the spectrum of light emitted by heated objects, refused to obey classical prediction. Calculations yielded absurd infinities, suggesting nature itself was breaking the rule. Physicists struggled to reconcile theory with observation, their confidence in classical determinism faltering like cracks spreading across a marble statue. Then, in 1900, Max Planck introduced a desperate, almost reluctant idea. Energy was not continuous but quantile. Instead of flowing smoothly like water from a faucet, it arrived in discrete packets quanta. To Planck, this was a mathematical trick to salvage the data, not a revolution. But revolutions rarely announce themselves with fanfare. They emerge quietly, unsettling the foundations until the edifice of certainty trembles. Planck's hypothesis was more than a technical fix. It suggested that reality itself might be grainy, indivisible at certain scales. Nature, once envisioned as infinitely divisible and infinitely predictable, began to look fragmented, discontinuous. Determinism, that proud inheritance from Newton, was no longer absolute. A shadow of uncertainty crept into physics, unsettling minds trained to see the cosmos as a perfect clockwork. Albert Einstein soon added fuel to this fire. In 1905, he proposed that light itself was made of quanta photon. This bold step explained the photoelectric effect, where light striking metal liberated electrons, but it also fractured the very nature of light. Was it a wave? Was it a particle? Classical physics demanded an answer, but quantum thought whispered something more disquieting. Perhaps it was both, or neither, depending on how one looked. The implications were staggering. If energy came in packets, if light itself defied singular categorization, then certainty was slipping away. Determinism no longer seemed a law etched into the bedrock of reality, but a fragile approximation. The tension was palpable. On one side, the comfort of Newtonian order. On the other, the rising tide of indeterminacy. The old guard resisted, clinging to continuity and predictability, while younger physicists dared to entertain a universe that operated by unfamiliar rule. By the 1920s, this tension erupted into a full-fledged revolution. Niels Bohr, Werner Heisenberg, and Erwin Schrödinger expanded upon Planck's spark, constructing a framework where probability replaced certainty. Heisenberg's uncertainty principle declared limits to what could be known. One could measure position or momentum, but never both with perfect precision. Reality was not a clock, it was a dice game, governed by probability distributions and hidden symmetries. This upheaval did more than rewrite equation. It unsettled philosophy, religion, even art. If the universe was not fully knowable, what did that say about human understanding? If chance lived at the heart of matter, then perhaps free will, creativity, and chaos were not anomalies, but intrinsic qualities of existence. The deterministic dream dissolved into a shimmering field of probability, leaving both awe and anxiety in its wake. Thus, the birth of quantum thought marked not just a scientific shift, but a profound cultural transformation. Humanity moved from a world where the future seemed calculable to one where mystery was embedded in the fabric of reality. Certainty had given way to uncertainty, and in that uncertainty, a new kind of wonder emerged. And from this wonder, the seeds of modern physics and deeper existential questions would grow. redefining the quantum realm. What if the very ground beneath reality is not solid, predictable, or even local, but a seething ocean of possibility? When physicists speak of the quantum, they are not describing some hidden dimension tucked away in a far corner of the cosmos. Instead, they point to the fundamental rules that underlie everything, the peculiar grammar by which existence writes itself. Unlike the classical world where cause leads neatly to effect, the quantum domain offers a far stranger script. Here, probability reigns, certainty evaporates, and entanglement stitches distant particles into ghostly unions that defy intuition. At its core, the quantum realm replaces absolutes with likelihood. A particle does not occupy a single position or carry a fixed momentum until observed. It exists instead as a shimmering cloud of probabilities described by a mathematical wave function. This means the future is not determined in advance but spread across countless possibilities, collapsing into a definite outcome only through measurement. For centuries, nature was imagined as clockwork, ticking with mechanical precision. The quantum rules shattered that vision, replacing the clock with a casino where dice are rolled at every instant. Equally unsettling is non-locality, the realization that quantum phenomena refuse to remain confined by space as we ordinarily understand it. A particle here can influence a particle there instantaneously, as if space itself were merely an illusion. This is no magician's trick, but an experimentally verified fact. Entangled particles, once connected, behave as though they share a single state regardless of distance. Einstein famously derided this as spooky action at a distance, yet modern experiments repeatedly confirm it. In the quantum realm, separation is a convenient fiction. At the deepest level, reality appears indivisible. Entanglement further challenges our assumptions about individuality. If two particles can exist as one system across vast spans, then perhaps the universe itself is bound together by hidden threads. In this view, the quantum world is not fragmented but profoundly holistic. What happens in one corner reverberates elsewhere, suggesting that the fabric of existence is woven from relationships rather than isolated parts. To understand the quantum is not to study objects but the invisible symphony connecting. Still, these principles are not confined to laboratory. They ripple out, shaping technologies and philosophies alike. Without quantum mechanics, there would be no semiconductors, no lasers, no computers, or even the screen on which you watch this. Yet beyond practical marvel, the quantum realm dares us to reconsider our place in reality. If outcomes depend on measurement, then observers are no longer passive spectators but participants in creation itself. The boundary between out there and in here blurs, raising questions about consciousness and the act of knowing. Thus, the quantum realm is less a destination and more a lens, a way of seeing existence anew. It forces us to abandon the comfort of deterministic order and embrace a reality both uncertain and deeply interconnected. While unsettling, this perspective opens profound possibilities. If probability, non-locality, and entanglement form the true scaffolding of the cosmos, then our classical world is but a surface appearance, a shadow cast by deeper law. In the chapters ahead, we will carry these principles as guideposts, for they illuminate paths into time travel, parallel world, and the very limits of knowledge. The quantum realm is not an escape from reality, but its most intimate foundation, a reminder that beneath the ordinary lie a mystery vast enough to reshape every story we tell about existence. The paradox of observation. Few experiments in the history of science have shaken our understanding of reality as profoundly as the double-slit experiment. At first glance, it appears almost childishly simple. Fire particles, whether bullets, marbles, or droplets of water, at a barrier with two narrow openings, and observe what pattern emerges on a screen behind it. In the everyday world, we expect a straightforward outcome. Toss pebble, and they pass through one slit or the other, creating two distinct bands. Waves, however, whether water or sound, behave differently. They spread, overlap, and interfere, creating a striking pattern of alternating light and dark bands like ripples colliding in a pond. Now comes the unsettling twist. When scientists performed this experiment with electron, tiny constituents of matter expected to behave like solid particles, the result defied expectation. Instead of forming two neat clusters, the electrons produced an interference pattern identical to wave. It was as if each electron passed through both slits simultaneously, interfering with itself before striking the screen. Matter, the very substance of our bodies and the stars, was behaving like a ripple in a medium no one could see. Skeptics might suspect some trick of numbers, perhaps electrons bumping into each other to generate the pattern. Yet the experiment worked even when electrons are fired one at a time, separated by long intervals. Each particle still paints its mark upon the screen, and gradually, dot by dot, the interference pattern emerges. The implication is staggering. Every single electron carries within itself the potential to act as both a localized particle and an extended wave. The universe does not demand it choose until the moment of observation. But what happens if we attempt peak? Suppose we place detectors at the slit to determine which path the electron takes. Instantly, the interference pattern vanishes. The electrons behave like ordinary particles again, choosing one slit or the other, producing two bands instead of many. Merely asking the question, merely observing changes the outcome. Reality, it seems, refuses to reveal itself fully until forced to. Observation is not passive quantum, it is an active participant in shaping event. This paradox, wave versus particle, interference versus certainty, illustrates the essence of quantum mechanics. It reveals a reality that does not exist in one clear form independent of us, but in overlapping states of potential until measured. To call this unsettling would be an understatement. It challenges the very notion of an objective universe ticking away beyond human perception. Einstein recoiled at such implications, calling it spooky, yet experiment after experiment confirmed the same strange truth. Photons, electrons, even large molecules obey these rules. The more carefully we probe, the deeper the mystery. Matter itself appears undecided, carrying within it both possibility until a conscious or mechanical observation collapses it into one. To the human imagination, raised on the clarity of classical mechanics, this feels like a riddle with no satisfying answer. How can something be both wave and particle? How can a single electron interfere with itself? And why does the universe seem to withhold its decision until the last possible moment? Perhaps the double-slit experiment unsettles us so deeply because it blurs the line between what is out there and what depends upon our act of looking. It forces us to admit that reality, at its most fundamental level, may not be independent of perception. In this sense, the experiment is not just physics, it is philosophy disguised as data. It tells us that the universe is not what it seems, and that even the simplest experiment can reveal truth stranger than imagination. Conscious versus measurement? What role does the act of looking play in shaping reality itself? The question haunts the foundations of quantum mechanics like an unresolved chord. In the laboratory, every experiment whispers a strange truth. Particles exist as clouds of probability until they are measured. Then the haze collapses into a definite outcome. But what triggers this collapse? Is it the physical act of detection or something deeper, the touch of consciousness itself? The Copenhagen interpretation, championed by Niels Bohr, suggested that measurement ends the uncertainty. According to this view, the measuring device interacts with the quantum system, forcing a single reality to crystallize. No human mind is necessary. The apparatus alone suffices. The universe in this framework is indifferent to whether a person watches the dial or not. Reality emerges through interaction, not through awareness. Yet this pragmatic approach left many dissatisfied. If probability waves collapse upon measurement, why do they not collapse earlier as particles bump into surrounding atoms? What exactly counts as a measurement? For some, these puzzles hinted that consciousness might be the missing piece. John von Neumann and Eugene Wigner speculated that the observer's mind could be essential, that consciousness itself was the ultimate measuring device. In their vision, reality remained unresolved until registered by awareness. This perspective unsettles because it places the human mind at the center of cosmic order. It suggests that without observation, the moon might not truly exist in a definite state. Such ideas blur the line between physics and philosophy, drawing us toward ancient debates about perception and reality. Are we discovering an external world or co-creating it through awareness? Detractors argue that invoking consciousness introduces mysticism into science. They point to decoherence theory, which explains collapse as an emergent effect. Particles interacting with their environment become entangled in vast networks, and probabilities average out into classical outcome. In this view, measurement is purely physical, requiring no mental spark. The Geiger counter clicks not because a human listens, but because atoms exchange energy inescapably. Consciousness, however fascinating, plays no special role, and yet the mystery lingers. Experiments like the delayed choice quantum eraser show that outcomes seem to depend on whether information could be known, even if no one actually observed it. This raises uncomfortable questions. Is potential knowledge enough to alter reality? Does the universe somehow anticipate awareness? The line between physics and metaphysics blurs in these shadow, leaving scientists and philosophers equally enthralled. For some, this tension represents two worldviews in conflict. On one side lies materialism, where the universe unfolds mechanically, indifferent to human presence. On the other lies a participatory cosmos, where mind and matter are entwined in ways we barely grasp. Neither path offers complete answers, and perhaps that is the point. Quantum mechanics resists final closure, as if inviting us to dwell in uncertainty. The debate stretches far beyond equation. If consciousness shapes reality, then human perception may hold cosmic significance. If it does not, then consciousness itself becomes another phenomenon to be explained by the machinery of nature, as incidental as a store or stone. Either interpretation forces us to confront unsettling questions about identity, agency, and the limits of knowledge. Thus, the riddle of measurement is more than a technical puzzle. It is a mirror held up to our deepest intuitions about existence. Do we stand apart from the universe, gazing upon it? Or are we threads woven into its fabric, our awareness as fundamental as light or gravity? The answers remain elusive, yet the very pursuit ensures the conversation between science and philosophy never ends. Reality without witness. Does the moon exist when no one looks at it? With this deceptively simple question, Einstein struck at the heart of quantum paradox. For him, reality must exist independently of our gaze. The universe, in his eyes, is not a trick of perception, but an objective stage that continues its performance whether or not there is an audience. If a tree falls in a forest and no one hears it, Einstein would argue, the crash still reverberates through the air, indifferent to human ear. This conviction reflected his broader realism. The cosmos is governed by laws that stand regardless of observation. Niels Bohr, however, countered with an unsettling proposition. Quantum phenomena have no definite properties until measured. For Bohr, speaking about reality as it is, apart from observation, is meaningless. A particle's location or momentum is not a fact waiting to be discovered, but a potential awaiting interaction. Observation, in this view, does not merely uncover reality, it crystallizes. Where Einstein demanded an objective world, Bohr insisted on a participatory one, shaped at its edges by acts of measurement. This clash of perspectives defined one of the most profound intellectual duels of the 20th century. To Einstein, Bohr's stance reduced science to mysticism, dissolving the very notion of an independent universe. He sought hidden variables, unseen mechanisms that might restore order and certainty. Bohr, on the other hand, embraced uncertainty as fundamental. He argued that the quantum description is complete, even if it refuses to align with classical expectations. Their debates were less about technical detail and more about the nature of existence itself. Modern experiments continue to tilt the scale. Bell's theorem and subsequent tests reveal that no hidden variable theory consistent with local realism can explain the behavior of entangled particles. These results appear to vindicate Bohr's view. The universe is not a pre-written script, but an unfolding dialogue between system and observer. Yet the implications remain hotly contested. fluid. Does this mean consciousness directly shapes reality, or is observer a stand-in for any interaction, say, a photon striking a detector? Philosophically, the stakes are immense. If Einstein was right, reality is robust, existing independently of mind. The universe is a cathedral built of matter and energy, awaiting our discovery, but indifferent to our present. If Bohr was right, reality is more like a poem, incomplete until read, its meaning co-authored by witness and world. One vision reassures us of a stable, objective cosmos. The other thrusts us into a participatory universe where certainty dissolves into probability. The tension between these views also shapes how we imagine us. Under Einstein's realism, we are explorers mapping a landscape that exists whether or not we survive to chart it. Under Bohr's quantum idealism, we are not merely explorers but participants woven into the act of creation. This subtle shift reframes the human role from detached observer to co-author of existence itself. Neither position has claimed absolute victory. Instead, the dialogue between them continues to guide inquiry. Quantum mechanics works with exquisite precision, yet its philosophical foundations remain unsettled. The moon likely does exist without witness, but at the deepest level, reality may not be so simple. Perhaps the truth lies between Einstein's cathedral and Bohr's poem, in a universe that is both independent and relational, both enduring and emergent. And as we move forward, this unresolved tension becomes more than neat philosophy. It becomes a compass. For the mysteries of time travel, parallel universes, and cosmic origins cannot be navigated without first confronting the haunting question: what, if anything, exists when no one is there to see it? Entanglement and the cosmic web. When Albert Einstein looked at the emerging framework of quantum mechanics, he marveled at its predictive power, yet bristled at its philosophical implication. Chief among his concerns was a phenomenon later termed quantum entanglement. To him, it suggested something almost supernatural, a violation of the cosmic speed limit he himself had established with relativity. He dismissed it as spooky action, at a distance, phrase that captured both skepticism and unease. For Einstein, the universe should be local, and deterministic events, separated by space, should not influence each other instantaneously. Yet entanglement appeared to defy principle. Entanglement arises when two or more particles are created in such a way that their states become linked. Measure one particle, and the other reveals a correlated outcome, regardless of the distance between them. For example, two electrons can share a property called spin. If one is measured and found to spin upward, the other, even light years away, will instantly reveal the opposite orientation. This eerie coordination happens faster than light could possibly travel, suggesting an interconnectedness that transcends space. To Einstein, such behavior meant the theory was incomplete, that hidden variable, unknown factors beneath the equations must secretly determine outcome. For decades, this idea lingered as an unresolved debate. Was quantum mechanics a complete description of reality, or merely a statistical facade concealing deeper law? The paradox seemed philosophical until physicist John Bell proposed a decisive test in the 1960s. His theorem outlined precise mathematical inequalities that any local hidden variable theory must obey. Quantum mechanics, however, predicted violation of those inequalities. If experiments matched the quantum predictions, hidden variables could not salvage Einstein's vision of locality. The stakes were monumental. Prove Bell wrong and quantum theory might collapse. Prove Bell right, and the universe itself would be confirmed as non-local in a way that shattered classical intuition. When experimentalists began testing Bell's inequality, the results were unambiguous. Time and again, quantum mechanics triumphed. No matter how carefully the setups were refined using photons, electrons, even atom, violations of Bell's limits consistently emerged. Nature was not playing by Einstein's rule. Entanglement was real, not illusion, and no hidden variables lurking in the shadows could explain it. To appreciate the gravity of this, consider what entanglement implies. Separate particles cease to exist as independent objects. Instead, they form a single, holistic system, even if torn apart by vast distance. Space does not sever their connection. Information does not flow between them in the conventional sense. Rather, their shared state transcends ordinary communication. It is as if the fabric of the universe itself ensures coherence between them. The phrase spooky action no longer feels dismissive but eerily accurate. Yet entanglement is not just a curiosity, it is a cornerstone of modern physics. It fuels quantum cryptography, enabling secure communication where any attempt at eavesdropping instantly reveals itself. It drives the architecture of quantum computers, where entangled qubits perform calculations unimaginable for classical machines. What began as Einstein's discomfort has evolved into one of the most powerful tools of 21st century science. Still, the philosophical tension remains. How can distant particles remain unified without exchanging signals? What does it mean for locality, for causality, for the very structure of reality? Some interpret entanglement as evidence that space itself is emergent, a byproduct of deeper connections beyond our perception. Others see it as a hint that information, not matter or energy, forms the bedrock of existence. Entanglement thus straddles paradox and revelation. On one hand, it contradicts our instincts about separation. On the other, it offers proof that the universe is profoundly interconnected. In this duality lies the enduring fascination. Einstein's unease reminds us that even geniuses resist truths that fracture intuition. Bell's theorem shows us that experiment, not preference, determines reality's rule, and entanglement itself whispers that the cosmos may be less like a machine, more like a vast web, where every thread resonates with distant echo. From paradox to principle, it challenged us to rethink not only physics, but our place within an inseparable whole. The universe as a unified whole. For centuries, science advanced by breaking the universe into parts. Reductionism became the guiding method to understand a complex system, divide it into smaller components, study each fragment, then reconstruct the whole. This approach gave us chemistry from atoms, biology from molecules, and technology from circuits. It created immense progress, yet it carried an implicit assumption that the universe could ultimately be explained as a sum of isolated pieces. Quantum entanglement shattered this tidy vision. In the 1930s, Einstein, Podolsky, and Rosen posed their famous paradox, arguing that quantum theory must be incomplete. They found it inconceivable that two particles, once interacting, could remain linked across vast distance. Yet experiments repeatedly confirm this very strangeness. Entangled particles behave as if connected instantly, no matter how far apart. Change the state of one, and the other knows immediately. Einstein dismissed it, spooky action at a distance. Today, we call it non-locality. Non-locality challenges the reductionist dream because it resists dissection. An entangled system cannot be understood by examining its individual parts. The meaningful reality resides in the relationship itself. The particles form a whole greater than their sum, bound by correlations that defy classical logic. Locality, the comforting idea that influences travel step by step through space, is not fundamental. The universe seems to operate with a deeper fabric where separation is an illusion. The implications reach beyond physics. If entanglement is woven into the structure of matter, then perhaps reality is not a collection of independent objects, but an indivisible network. This resonates with holistic philosophies that have long spoken of interconnectedness, from Eastern traditions to ecological thought, where reductionism isolates, entanglement unifies. It suggests that the universe is not a machine of cogs, but a tapestry where threads only make sense together. Decoherence, quantum teleportation, and Bell's theorem provide empirical grounding for this vision. Bell's experiments, repeated across decades with increasing precision, consistently show that entangled correlations violate classical expectation. No hidden variables, no local signals can explain the result. What emerges is undeniable. Quantum systems behave as unified wholes, even when stretched across galaxies. To reductionists, this feels unsettling. The very act of cutting systems apart, once the key to knowledge, seems to dissolve meaning. But to those open to holistic interpretations, entanglement offers a profound revelation. The universe is relational. Existence is not built from solitary entities, but from connection. Identity, whether of particle or people, is inseparable from the networks they inhabit. This vision also challenges how we see ourselves. If the universe is fundamentally entangled, then consciousness, life, and matter may not be separate categories, but expressions of a unified order. The boundary between observer and observed, subject and object, begins to blur. Our sense of isolation could be a perceptual illusion, a convenience of classical thinking rather than a description of reality. Philosophically, non-locality raises haunting question. Does it imply instantaneous communication beneath space and time? Or is it evidence that distance itself is not primary but emergent from a deeper structure? Some physicists speculate that space-time itself may arise from quantum entanglement, that geometry and gravity are consequences of the invisible bond. If true, then the universe is not merely connected, it is connection incarnate. Still, mystery remains. Entanglement reveals correlation, not causation. It does not permit faster-than-light messages or magical control. Its unifying power is subtle, more like harmony in music than wires carrying signal. Yet this subtlety does not diminish its significance. It forces us to rethink the foundations of reality, to acknowledge that the pieces cannot be fully known without the whole. Thus, the contrast between reductionism and holism is not merely methodological, it is existential. Reductionism gave us precision, but entanglement gives us context. One isolates, the other integrates. Together they may point toward a richer science, one that honors both parts and whole. And in this balance we glimpse a universe where everything is bound together not by chance, but by the profound architecture of non-locality. Entanglement beyond physics. Imagine two minds separated by ocean, yet sensing the same thought at the same instant. Lovers who finish each other's sentence. Friends who feel unease without a call. Cultures that independently invent the same myth. These moments feel uncanny, as though some invisible thread links us across space and time. In science, quantum entanglement describes particles bound so tightly that distance cannot sever their connection. Could this principle extend beyond physics into the realm of consciousness, love, and human meaning? Physicists caution against easy metaphor. Entanglement, in strict terms, is a mathematical correlation observable under controlled conditions. It does not transmit messages, nor does it operate through mystical channel, yet the allure persists. For entangled particles, measurement of one instantaneously defines the other, regardless of separation. This scientific fact echoes the intuition that human beings, too, may be bound in ways not reducible to biology or chance. Philosophers have long sought language for this unseen connectivity. Mystics speak of the unity of all life, poets of souls woven together, psychologists of unconscious resonance. These traditions, though not identical to quantum mechanics, converge on a single theme. Relationships shape reality more deeply than isolated entities ever could. In this sense, entanglement becomes a metaphor, a reminder that existence may be less about solitary act and more about shared pattern of being. Consider consciousness. Some theorists speculate that the mind itself may display quantum properties, perhaps through entangled states within neural processes. Though controversial and unproven, such ideas stir fascination because they suggest awareness could be fundamentally relational. If true, then thoughts, emotions, even identity might not arise solely within individuals, but in networks of connection that stretch beyond the skull. Consciousness would not merely observe entanglement, it would embody it. Love, too, finds resonance here. To love deeply is to feel another's joy and suffering as though it were your own. This collapse of boundaries mirrors entanglement's refusal to honor distance. Neuroscience explains empathy through mirror neurons and hormonal chemistry, but metaphorically, love feels quantum, instantaneous, non-local, transcending rational calculation. Entanglement thus becomes a poetic lens through which we interpret bonds that defy explanation. Yet metaphors carry both power and peril. To conflate quantum mechanics with spirituality risks distorting science. The task is not to claim entanglement explains love or consciousness, but to acknowledge how it inspires reflection. Where physics demonstrates a cosmos knitted by correlation, philosophy imagines a human story within that fabric. Both approaches enrich our understanding, one through precision, the other through metaphor. In the end, entanglement beyond physics is not a literal claim, but a narrative divide, a bridge linking scientific wonder to lived experience. It invites us to ask whether the universe mirrors our longing for connection, whether the same principles that unite particles whisper through the chamber chambers of our heart. Perhaps we seek in physics not just equations but affirmation that isolation is an illusion. This does not diminish scientific rigor, it expands its resonance. Entanglement reminds us that relationships, whether between particles or people, are the true architecture of reality. In its mystery, we glimpse both the exacting clarity of mathematics and the boundless poetry of human connection. As we continue, the metaphor of entanglement becomes a tool for navigating not only quantum puzzle, but existential one. For what is the universe if not a tapestry of intertwined destinies, binding stars, atoms, and souls into a single, inseparable whole? Time in the quantum mirror. Time as we experience it feels like an unstoppable current carrying us forward. A glass shatters on the floor, but never leaps back together. A flame consumes paper, but never reconstructs it from smoke and ash. This irreversibility, so obvious in daily life, is enshrined in the second law of thermodynamics. Entropy, the measure of disorder, tends always to increase. From the decay of stars to the cooling of coffee, nature seems to obey this one-way directive. This is the arrow of time, the reason we remember the past but not the future, and why aging feels inexorable. Yet when physicists examine the quantum level, a startling contradiction emerges. The fundamental equations governing particles do not prefer one temporal direction over the other. Schrödinger's equation, which describes the evolution of a quantum system, is perfectly reversible. In principle, if you knew a system's wave function completely, you could run the mathematics backward and recover its past with the same ease as projecting its future. Unlike broken glass, quantum states do not inherently forbid reversal. This contrast produces a profound tension. If the building blocks of reality are reversible, why is the world we inhabit so stubbornly irreversible? One explanation lies in the scale of observation. Individual particles evolve smoothly, but once vast numbers interact, entropy takes hold. A single molecule of air box can be tracked backward and forward, but trillions colliding together create such complexity that reversibility dissolves into practical impossibility. The arrow of time is less about fundamental laws and more about statistics, the overwhelming likelihood that systems evolve from order to disorder. Still, quantum theory introduces twists that complicate the story. Quantum superpositions, where particles exist in multiple potential states, seem reversible until measurement occurs. Observation collapses possibilities into one outcome, erasing alternatives. That act is irreversible. Information once discarded cannot be perfectly retrieved. This suggests the boundary between reversibility and irreversibility may hinge on observation itself, blurring physics with philosophy. Experiments in quantum computing reinforce this paradox. Qubit, insulated from noise, can evolve forward and backward as equations predict. Algorithms deliberately rewind states, reversing operations like a cosmic undo button. For brief windows, the arrow of time seems suspended, but the slightest interference from the environment's stray radiation, thermal vibrations destroys coherence. Entropy rushes back in, restoring irreversibility. What happens in pristine isolation rarely survives contact with reality's messy openness. Some physicists speculate that reconciling these perspectives may reveal new insights into the fabric of time. Perhaps irreversibility is emergent, not fundamental, a shadow cast by complexity. Perhaps time's arrow is tied to the expansion of the universe itself, entropy increasing as space unfurls. Others wonder whether information is never truly lost, only scrambled beyond recognition, hinting at deeper laws yet to be uncovered. For us, the contrast is both humbling and awe-inspiring. The irreversible march we feel in our bone may be a macroscopic illusion, an emergent phenomenon riding atop reversible micro-law. Beneath the certainty of clocks ticking lies a symmetry where past and future are mathematically indistinguishable. The dissonance between these two realities forces us to question whether time is as absolute as we assume, or whether it is a construct born of perspective, scale, and the limitations of memory. Thus, the arrow of time and quantum reversibility coexist uneasily, one ruling our daily lives, the other governing the universe's smallest scale. To grasp both is to recognize that what feels inevitable may not be fundamental, and what seems reversible may collapse under scrutiny. It is within this tension that some of the deepest mysteries of existence reside. Quantum superposition of pasts and futures. What if the future could reach back and touch the past? In classical thinking, time flows in one direction. Yesterday shapes today, today shapes tomorrow. But quantum mechanics often treats time less like an arrow and more like a labyrinth. At its heart lies superposition, the principle that a system does not choose a single state until measured. If position, spin, or momentum can exist in multiple possibilities at once, could time itself behave the same way? Could events stretch across past and future, suspended until observation fixes their story? Experiments suggest this may not be a fantasy. The delayed choice experiment, inspired by John Wheeler, demonstrates that the decision of how to measure a particle can seemingly influence its prior behavior. Light traveling through an interferometer behaves like a wave or a particle depending on the setup. Astonishingly, the choice to alter the setup can be made after the photon has already entered the system, yet the outcome retroactively aligns with the later decision. It is as though the photon's path remains undetermined until the future. Measurement locks it in. Quantum eraser experiments extend this idea further. In these setups, information about a particle's path can be erased or preserved even after detection. When path information is erased, interference patterns reappear, as though the particle's past trajectory had never been decided. The suggestion is provocative. History at the quantum level is not fixed but malleable, contingent upon what can be known in the future. This unsettling possibility challenges our deepest intuition. We are accustomed to thinking of cause preceding, effect of memory following event, yet quantum phenomena whisper that the border between past and future may not be so rigid. Some interpretations even suggest that quantum states exist in a kind of time-neutral haze, where probabilities flow forward and backward simultaneously, collapsing only when observation selects a consistent narrative. Does this mean the future literally shapes the past? Perhaps not in the ordinary sense. What the experiments reveal is that the quantum realm resists our linear storytelling. Instead of a chain of causes leading to effect, events may exist as interwoven possibilities, extending across temporal boundaries. Measurement stitches them together into coherent, but until then, past and future alike remain open. Such notions invite both awe and unease. If the universe operates with two-way traffic across time, then determinism and free will take on new shades of meaning. Our choices today might ripple backward, influencing what was, just as past conditions ripple forward into what will be. Reality becomes less a line and more a web, where time is not a stage but a participant in the drama. The implications extend beyond physics into philosophy. If past and future interweave, then memory and anticipation could be two sides of the same coin. Consciousness itself may experience time sequentially, but perhaps the quantum fabric holds all sequences in suspension, waiting for awareness or interaction to crystallize a single flow. The now becomes less a point on a line and more a bridge across potential histories and futures. Still, caution tempers speculation. Quantum experiments do not hand us paradoxes of changing history in the cinematic sense. They show instead that our categories before and after, cause and effect, may be approximations, useful but incomplete. Beneath them lies a subtler order, where superposition encompasses not only space but time. Thus, quantum mechanics confronts us with a humbling possibility that reality is stitched from threads of possibility extending in both directions, and that what we call the past may be as provisional as the future. In this light, time itself becomes a superposition, an unfolding mystery awaiting its collapse into the story we tell. Time travel and the quantum realm. Time travel has long been the playground of imagination, from H.G. Wells' Time Machine to cinematic portals that whisk heroes between between centuries, fiction paints it as a journey through history, stepping into the past or leaping into the future as easily as crossing a room. Yet when science peers into this dream, the story becomes far stranger. The quantum realm, with its probabilistic laws and counterintuitive structures, offers hints that time may not be the rigid arrow we assume, but a pliable dimension capable of loops, fold, and paradox. Classical relativity provides the first scientific foundation for this idea. Einstein's equations permit closed, time-like curves path through space-time that loop back upon themselves. In theory, an object following such a curve could meet its past self. Wormholes, if stabilized, might serve as shortcuts through space-time, enabling journeys not just across vast distances but across eras. Still, these concepts remain precarious, demanding conditions exotic matter with negative energy, colossal gravitational field that may never exist outside equation. Quantum mechanics deepens the intrigue. Some theorists suggest that closed time-like curves could coexist with quantum principle, though in peculiar ways. For instance, a particle traveling back in time might interact with its earlier version, yet consistency conditions would prevent paradoxes like killing one's grandfather. Quantum theory, in this sense, acts as a cosmic editor, ensuring logical coherence even when causality bends. This vision transforms time travel from chaotic fantasy into a structured, though alien, possibility. Science fiction revels in the paradoxes, characters rewriting history, colliding with alternate selves, reshaping futures. The quantum approach, however, reframes these scenarios. Instead of wild alteration, the universe might enforce self-consistency. Whatever happened must happen. A traveler returning to the past could influence events, but only in ways that preserve the timeline. In this view, free will becomes constrained, not erased. One can act, but only along paths that sustain coherence. The drama lies not in rewriting history, but in realizing how tightly it binds us. Yet another quantum interpretation points elsewhere. Rather than a single consistent timeline, time travel might fracture reality into many branches. The many-world interpretation suggests that each action generates a new universe. Travel to the past would not alter your own history, but create a divergent one, leaving the original intact. Paradoxes dissolve, replaced by infinite proliferations of reality. What science fiction calls alternate histories become, in this model, genuine universes sprouting endlessly from quantum choices. These possibilities blur the line between speculation and rigorous physics. While experiments cannot yet probe closed time-like curves or branching universes, the mathematics remains consistent enough to keep the questions alive. Importantly, quantum mechanics forces us to consider that time is not absolute, not fixed, but deeply entangled with uncertainty and possibility. The same framework that allows particles to exist in superposition might allow timelines themselves to coexist in superposed state. For the dreamers, this means time travel may never be reduced to a gleaming machine with dials and levers. Instead, it might emerge from the very strangeness of quantum law, a feature of a universe more complex than our linear intuitions allow. Whether by loops of space-time, enforced consistent, or branching work, the quantum realm ensures that time is not merely a prison, but a frontier. As we move forward, the question becomes less whether time travel is possible and more what it reveals about reality itself. In pursuing the quantum pathways of time, we confront not just the mechanics of movement, but the meaning of memory, destiny, and existence across worlds, multiverses, and infinite possibilities. When faced with the riddles of quantum mechanics, one of the most enduring puzzles has been the so-called collapse of the wave function. According to the traditional Copenhagen interpretation, a particle exists in a superposition of possibilities until observed. The act of measurement forces the universe to choose one outcome, discarding all others. An electron is here or there, a photon passes through one slit or the other, and the ambiguous haze of probabilities collapses into a single reality. This view, though widely taught, leaves profound questions unanswered. Why should observation hold such privilege? And what happens to the unrealized possibilities that seemed equally valid before the collapse? In 1957, a young physicist named Hugh Everett proposed a radical alternative. Instead of assuming collapse, he suggested that all possible outcomes occurred just not in the same branch of reality. Each measurement splits the universe into multiple versions, each containing a different result. If you flip a quantum coin, one universe records heads while another contains tail, both as real as the one you perceive. The cosmos, under Everett's interpretation, becomes an ever-branching multiverse where every potential path is realized. This vision transforms the role of observation. The observer does not collapse the wave function but becomes entangled with it. In one branch, you see the particles spin up. In another, you see it spin down. Both versions of you continue forward, unaware of the divergence, each convinced theirs is the only outcome. Reality is no longer a single thread, but an expanding tree of branching history growing richer with every quantum event. To many, this idea borders on science fiction. Infinite universes constantly multiply, each containing alternate version of ourselves making different choices. It sounds more like narrative fantasy than sober physics. Yet Everett's hypothesis demands no additional mechanisms beyond the equations already in place. In fact, it removes the ad hoc notion of collapse entirely, treating the Schrödinger equation as universally valid with no exception. Simplicity, not extravagance, is its strength. The implications, however, are staggering. If true, then everything that could happen does happen somewhere in the multiverse. Every path not taken, every unspoken word, every unsaved life, every unrealized future unfolds in a parallel branch. Our sense of uniqueness dissolves, replaced by a vast ocean of alternate selves living out diverging fate. For some, this evokes awe; for others, existential vertigo. Critics argue that the many worlds hypothesis is extravagant precisely because it multiplies realities beyond necessity. They question whether universes that cannot be observed directly should count as science. If every possibility occurs, what predictions does the theory truly make? And yet supporters counter that many worlds provides a coherent, collapse-free account that aligns perfectly with quantum mathematics. Experimental evidence may not distinguish it easily, but its conceptual clarity makes it an enduring contender. In recent decades, the hypothesis has found new relevance. Quantum computing, for example, exploits superposition to perform calculation, as though many outcomes coexist. Some enthusiasts describe this as borrowing power from parallel worlds, though others caution such language is metaphorical. Still, the success of technologies built on superposition lends indirect weight to the notion that possibilities are not merely abstract, they are functionally real. Philosophically, many worlds reshapes our conception of fate and free will. If every decision branches the universe, then no choice extinguishes its alternative. Somewhere, every possibility unfolds. The self we identify with is merely one among countless versions. This perspective can be unsettling. What meaning does responsibility hold if other selves carry out opposite actions? Yet it can also be liberating, suggesting that reality's richness is not confined to a single fragile thread. Ultimately, Everett's branching cosmos invites us to reconsider what real truly means. Collapse gives us a singular universe, neat and familiar, but burdened with unanswered questions about observation. Many worlds offers a grander stage, dizzying in scope, where no possibility is wasted. Between these interpretations lies a tension that continues to animate both physics and philosophy. Is reality singular and selective, or infinitely branching and inclusive? Infinite reality, infinite self. What if every choice you make, every hesitation, every possibility that flickers in your mind spawns another version of you living out the road not taken? The multiverse hypothesis suggests this is more than poetic musing. Quantum theory's many worlds interpretation, proposed by Hugh Everett in the 1950s, imagines that every quantum event branches into countless universes. In one, the photon passes through the left slit. In another, it takes the right. Extend this logic, and every decision in your life blooms into parallel selves scattered across an infinite landscape of reality. The implications are staggering. Somewhere there is a you who never left your hometown, another who moved across the world, another who never met a certain friend, another who died young. Each of these versions is as real as the one reading these words, each following a thread woven from quantum probability. Identity, once anchored in a single narrative, dissolves into a vast multiplicity. Who then are you? Philosophers grapple with the existential weight of this idea. If infinite versions of you exist, does individuality lose meaning, or does it take on new depth, each self representing one facet of a cosmic spectrum? Some argue that the self is not diminished but expanded, that you are not confined to a single life story, but are instead a constellation of possibility. Like light refracted through a prism, identity may scatter across universes, each ray distinct yet part of a larger whole. Yet there is unease in this vision, for if you are infinite, which one is truly you? Is the you who achieved your greatest dream more authentic than the you who failed? Are the joyous, the tragic, the forgotten selves equally valid? The multiverse complicates the comfort of uniqueness, forcing us to confront the fragility of what we call I. Perhaps the self is not a singular flame, but a firework exploding into countless sparks across the dark. Psychologically, this notion cuts deep. Many of us cling to regret choices not made, opportunities lost. The multiverse offers both solace and torment. Somewhere, you did take that leap, you did mend that relationship, you did become the person you imagined, but somewhere else you faltered worse than you ever did here. Infinity holds both redemption and despair, an endless gallery of mirrors reflecting not only your triumphs but also your failures. Existentially, the idea reshapes free will. If all choices are realized somewhere, then choice itself becomes less about determining outcome and more about determining which version of you experience. You are not choosing between realities, you are selecting which self becomes your conscious continuation. Responsibility still matters, but its frame expands. Your decisions do not erase other possibilities, they simply decide which branch you will inhabit. From a cosmic perspective, the multiplicity of selves mirrors the multiplicity of the universe itself. Just as galaxies scatter across the void, so do identities scatter across reality. Entanglement, non-locality, superposition all suggest a cosmos where separateness is provisional. Perhaps the multiverse is not a collection of disconnected worlds, but a larger, unified organism in which you are simultaneously many. Art and literature have long played with these themes: parallel lives, sliding doors, infinite narrative. Science now lends them weight. Experiment in quantum mechanics do not prove the many worlds interpretation, but they leave open the possibility, and in that possibility, imagination stretches toward infinity. Ultimately, the question may not be whether multiple versions of you exist, but how to live in light of the possibility. If identity is infinite, then each moment here acquires a special poignancy. You are one expression of a vast chorus, singing in harmony across dimension. This self, this life, may be fleeting, but it is no less precious. The awareness, reading these words, is not diminished by infinite alternative, it is illuminated by them. Cosmology meet quantum. Infinity has always haunted cosmology. Look far enough into the night sky, and the mind begins to wonder, is our universe unique or merely one of countless others? Modern science entertains both possibilities through two distinct yet strangely resonant frameworks. On the cosmic scale, inflationary theory suggests that our universe is but a bubble within an endless froth of expanding space. On the quantum scale, the many worlds interpretation proposes branching realities where each quantum decision births a new universe. Both visions confront us with infinity, yet from different vantage points, one vast and physical, the other subtle and mathematical. Cosmological inflation begins with the Big Bang, but quickly diverges. According to theory, fractions of a second after the initial explosion, space expanded at unimaginable speed. This inflation smoothed the cosmos and seeded galaxies, but it may not have stopped stopped everywhere. Regions could continue inflating, spawning endless bubbles, each forming a universe with its own law. From this view, the multiverse is a cosmic archipelago with islands of reality floating in an infinite sea of expansion. Our universe, with its galaxies and life, is merely one such island among uncountable others. Quantum mechanics paints infinity differently. The many worlds interpretation proposed by Hugh Everett insists that every quantum event generates branching outcome. A particle takes two paths, and both unfold each in a separate universe. In this scheme, reality does not collapse into one outcome, but proliferate endlessly. Your life itself, under this model, exists in countless variations. One where you chose differently this morning, another where history unfolded along divergent lines. Here, infinity is not cosmic geography, but the relentless flowering of possibility at every instant. Though arising from different theories, these two visions resonate. Both challenge the notion of a singular universe. Both insist that what we perceive as reality is but a slice of a greater whole. Yet their infinities differ in texture. Inflationary bubbles are vast, spatially distinct realms, possibly inaccessible forever. Quantum branches, in contrast, are stacked atop each other, layered possibilities existing in superposition until measurement divides them. One infinity sprawls across space, the other across probability. The philosophical consequences are staggering. If inflation's multiverse is real, then somewhere out there lies a universe nearly identical to ours, save for a single variation. A different arrangement of galaxies, a world without Earth, or a version where life never arose. If quantum branching is real, then every possibility plays out simultaneously, and your other selves walk countless parallel roads. In one infinity, the cosmos repeats endlessly outward. In the other, it multiplies inward through the fabric of quantum law. Skeptics argue that both visions flirt with the untestable. If we can never access other bubbles or other branches, can they truly count as science? Yet even critics admit these models emerge naturally from equations already trusted in cosmology and quantum mechanics. They may be extrapolation, but they are not fantasy. The mathematics forces us to grapple with infinities, whether or not we find comfort in. Taken together, the cosmological and quantum multiverses frame a universe that is anything but singular. We may inhabit an island within an archipelago, and simultaneously one branch of a ceaselessly branching tree. Infinity surrounds us from both directions, outward into space, inward into possibility. As we journey further, this dual vision of infinity sets the stage for the deepest question. If realities are endless, what does it mean to be this particular version of ourselves in this fleeting universe at this exact moment in cosmic time? Quantum technology and human destiny. For centuries, human progress has been measured by our ability to calculate. From the abacus to silicon processors, every leap in technology has hinged on our capacity to process information faster and more efficiently. Classical computers, which define the world, are built on binary logic, streams of bits that can exist only as 0 or 1, off or on. Through layers of transistors and circuits, these binary states combine to perform astonishing feats, from simulating galaxies to streaming a film. Yet, as powerful as they are, classical machines remain bound by their linear logic. They explore problems one possibility at a time, marching deterministically through sequences of yes or no. Quantum computing enters this landscape as something entirely different, not an incremental improvement, but a paradigm shift. At its core lies the principle of superposition. A quantum bit or qubit is not restricted to being solely 0-1. Instead, it can exist in a blend of both simultaneous, a probabilistic state described by amplitude. When harnessed, this means a quantum processor can explore multiple possibilities at once, parallelizing calculations in ways a classical system cannot. The result is exponential potential. A modest number of qubits can, in theory, outperform the largest supercomputers. Equally transformative is entanglement. When qubits are entangled, the state of one is inseparably linked to the state of another, no matter how far apart. Change the first, and the second responds instantly. In computation, this allows quantum machines to coordinate information with a cohesion unimaginable in classical circuits. Instead of independent switches, qubits act like like members of a perfectly choreographed dance, their correlations encoding solutions that transcend linear logic. To grasp the contrast, consider a search problem. A classical computer tests possibilities one after another, narrowing toward an answer step by step. A quantum computer, by leveraging superposition and entanglement, evaluates many routes simultaneously, collapsing upon measurement to reveal the solution with dramatically fewer steps. Algorithms such as Shaw's, which threatens current cryptography by factoring large numbers efficiently, and Grover's, which accelerates searches, illustrate the disruptive promise of this new paradigm. But quantum computing is not simply about raw speed, it is about reimagining what calculation means. Where classical logic demands determinism, quantum logic embraces uncertainty as a resort. The very properties that unsettled Einstein's superposition, entanglement, probabilistic outcomes become the fuel of computation. It is as if the universe's own ambiguity has been turned into a tool, transforming paradox into power. Still, this revolution is not without obstacle. Qubits are fragile, easily disturbed by their environment. A stray vibration, a thermal fluctuation, or cosmic radiation can collapse superpositions prematurely, introducing errors. To combat, researchers pursue error correction technique, building layers of redundancy into fragile state. Quantum hardware requires extreme isolation, often cooled to temperatures colder than outer space, to preserve coherence. These challenges make building large-scale, practical quantum computers one of the most formidable engineering tasks of our age. Yet progress continues. Laboratories worldwide now demonstrate prototypes with tens or hundreds of qubits, inching closer to the threshold of quantum advantage, the point where a quantum machine outperforms classical computers at meaningful tasks. Governments and corporations invest billions, recognizing that breakthroughs here could reshape fields from drug discovery to climate modeling, from artificial intelligence to secure communication. The contrast, then, is stark. Classical computers march in binary certainty, while quantum computers thrive in ambiguity. Where one eliminates uncertainty to compute, the other embraces it, weaving probabilities into solutions. In this inversion lies the promise of a technological revolution, one that transforms the unsettling strangeness of the quantum world into practical capability. Quantum communication and security. Every age has its codebreakers, from the ciphers of ancient generals to the algorithms of modern intelligence agencies. Secure communication has always been a fragile shield. Classical communication, no matter how clever, is vulnerable in principle. A determined adversary, armed with enough computational power or time, can break through. Encryption becomes a race, a temporary lock waiting for a stronger key. But what if communication could be rendered unbreakable, not by human ingenuity alone, but by the laws of nature themselves? Quantum mechanics offers such a possibility. The same principles that once disturbed physicists, superposition, uncertainty, entanglement, are now being harnessed to create a revolution in security. At the heart of quantum communication lies a striking truth. Observation disturbs the system. If a photon is used to transmit information, any attempt to intercept or measure it inevitably changes its state. Unlike classical bits, which can be copied undetected, quantum bits or qubit betray eavesdropping by their very nature. This principle forms the foundation of quantum key distribution, or QKD. Imagine two parties, traditionally called Alice and Bob, attempting to share a secret key. They transmit qubits, often encoded in the polarization of photons across a channel. If no one interferes, Alice and Bob's measurements align, creating a shared, random key. But if an eavesdropper Eve tries to intercept, the act of measuring scrambles the results, introducing detectable errors. Security is guaranteed not by computational complexity, but by quantum law itself. Contrast this with classical encryption. Today's strongest codes depend on problems like factoring enormous number, tasks that would take conventional computers impractically long to solve. Yet quantum computers, if fully realized, could slice through these barriers with terrifying efficiency. Classical security, once thought nearly invincible, now faces obsolescence. Paradoxically, quantum mechanics both threatens old cryptography and provides the tools for a stronger future. The implications extend beyond spy game. In a world increasingly dependent on digital networks, financial systems, healthcare record, global infrastructure, the vulnerability of communication is not academic. A breach could destabilize economies, compromise privacy, even endanger lives. Quantum communication promises a new architecture of trust, where secrecy is not a matter of difficulty, but of physical impossibility. Already, prototypes are emerging. Quantum-secure networks have been demonstrated across cities, continents, even satellites. In 2017, China's Missia satellite successfully enabled quantum-encrypted communication between ground stations thousands of kilometers apart, marking a milestone in the dawn of a quantum internet. While still experimental, these achievements foreshadow a world where secure communication is woven into the very fabric of global interaction. Philosophically, this shift is profound. For millennia, humans have played cat and mouse with secrecy and exposure, creating locks and picking them, encoding messages and decoding them. Quantum security changes the rules of the game entirely. No longer is safety provisional, dependent on cleverness or chance. Instead, it arises from the bedrock of reality itself. Eavesdropping becomes not just impractical, but metaphysically impossible without detection. And yet new questions emerge. If communication becomes unbreakable, how might power shift in politics, economics, and warfare? Who will control the infrastructure of this quantum web? Does invulnerability to interception also create new risks of unchecked secrecy? As with all revolutions, the promise comes entwined with uncertainty. What is clear is that quantum communication marks a turning point. Where classical systems fracture under the pressure of progress, quantum systems transform vulnerability into resilience. It is a reminder that the very features of the universe that once baffled scientists, the strange dance of particles at the smallest scale, can also serve as guardians of trust in a digital age. In their paradox, they carry both mystery and promise, binding the abstract world of quantum theory to the tangible needs of human society. Quantum technology and human evolution. Throughout history, each leap in technology has not merely changed our tool, but redefined what it means to be human. Fire reshaped survival. Writing preserved memory beyond generation. Electricity rewired civilization. Now, quantum technology stands at the threshold, promising to alter intelligence, society, and destiny itself. If classical machines amplify strength and logic, quantum devices amplify possibility, harnessing superposition, entanglement, and uncertainty to expand the boundaries of thought and action. Quantum computing is often described as brute calculation power, but its essence is subtler. Unlike classical bits that are rigidly 0 or 1, qubits inhabit superposition, exploring many paths at once. For problems in chemistry, cryptography, or artificial intelligence, this means not just faster answers, but fundamentally new mode of reasoning. Such machines could simulate molecular complexity with precision beyond today's reach, opening doors to medicines, materials, and energies once confined to speculation. In amplifying our problem-solving capacity, quantum computing becomes less a tool and more a partner in creativity. Yet technology never exists in isolation. Quantum communication, exploiting entanglement or unbreakable encryption, could reshape trust itself. A civilization where information cannot be intercepted or forged alters the fabric of politics, commerce, even personal relationships. Secrets may become inviolable, surveillance obsolete, and institutions forced to evolve under new assumptions about privacy, power. The very architecture of society bends when information, the bloodstream of civilization, flows under quantum rule. At a deeper level, quantum technology challenges our concept of intelligence. Artificial intelligence, when fused with quantum hardware, may transcend human limitations not only in speed but in style. Imagine an intelligence that does not follow single threads of reasoning, but inhabits a cloud of probability, navigating multiple realities simultaneously. Such systems might develop strategies we cannot fathom, nudging us towards symbiosis. Rather than competition, the question ceases to be whether machines will outthink us and becomes how partnership with them will redefine thinking itself. For humanity, the stakes extend beyond economics or efficiency. Quantum technology may act as a mirror, revealing that uncertainty and interconnection, the very features we once saw as flaws in ourselves, are engines of growth. If reality is probabilistic, then creativity, imagination, and risk are not aberrations, but expressions of the universe's deepest logic. To evolve alongside quantum machines is to embrace that truth, integrating chance and correlation into how we live, govern, and dream. Of course, peril shadows promise. A society divided by access to quantum tools risks new hierarchies of power, where those who command such technology steer the trajectory of civilization. The capacity to decrypt, simulate, or optimize at unprecedented scales could amplify inequality if hoarded by the few. Human destiny hinges not only on invention, but on wisdom. Whether we distribute these tools shared inheritance or wield them as instruments of control. Ultimately, quantum technology is not just machinery. It is a catalyst for reimagining humanity. It invites us to conceive of intelligence as collaborative, society as interwoven, and destiny as open-ended. Just as fire taught us to reshape nature and writing taught us to reshape memory, quantum mechanics now teaches us to reshape possibility itself. As we step into this frontier, the question is not whether quantum technology will change us. It already has. The true question is, into what kind of species will we allow it to transform us? Existential reflection. Among the deepest questions raised by quantum mechanics is whether the universe exists independently of us, or whether our observation plays an active role in shaping it. The classical worldview leaves little room for ambiguity. The cosmos is governed by predetermined laws, unfolding inexorably regardless of who or what happens to what. The planets do not orbit because we gaze at the night sky. They orbit because gravity demands it. Within this paradigm, human agency is reduced to the act of witnessing a grand, impartial theater. Quantum mechanics unsettles this certainty. The double-slit experiment demonstrates that particles behave as probabilities until measured, collapsing into specific outcome only when observed. Does this imply that the universe waits for consciousness to intervene, choosing path only when compelled by attention? Or is observation merely another physical interaction, no different from a photon scattering off an atom? The line between passive spectator and active creator becomes blurred. Some interpretations, like the Copenhagen view, lean toward the radical. They suggest that reality does not exist in a definite form until it is observed, as though the act of measurement pulls one version of the universe from a haze of possibility. If true, then our role is not merely descriptive, but generative. We do not just record reality, we help bring it into being. This prospect electrifies the imagination, implying that consciousness and cosmos are entwined at the deepest level. Others resist such conclusion. The many worlds interpretation, for instance, denies collapse entirely, asserting that all outcomes occur, branching into parallel universe. In this framework, our perception merely selects one branch of an ever-expanding multiverse. Reality exists in its fullness, regardless of what we. Our awareness does not create outcomes, but merely discovers them. This view restores determinism at the cost of multiplying reality beyond measure. Einstein himself was uneasy with the suggestion that observation could dictate existence. He famously quipped, "Do you really believe the moon is not there if you are not looking at it?" His discomfort reflects a fundamental tension. Intuition rebels against the idea that reality depends on our gaze, yet experiment after experiment reveals a peculiar truth. Systems remain undefined until measured. Whether this indeterminacy arises from epistemic limits or genuine ontological ambiguity remains unresolved. Philosophers and physicists alike wrestle with the implication. If consciousness does shape reality, even at the quantum level, then the universe may not be an indifferent machine, but a participatory cosmos. Human beings, and perhaps all sentient observers, would stand not outside of reality, but within its very machinery, co-creators in the unfolding of existence. Such a view resonates with ancient philosophy that saw perception and being as inseparable. On the other hand, the argument for predetermined universal laws carries equal weight. The equations of quantum mechanics operate with or without observed. Particles interact, stars ignite, galaxies evolve, long before life emerged on Earth. To assume that the cosmos requires our awareness risks anthropocentrism on a cosmic scale. Observation may simply be another form of physical interaction, collapsing probabilities not because of consciousness but because of contact. Reality would then remain fundamentally indifferent, its laws absolute, with our awareness merely incidental. Perhaps the truth lies somewhere in between. The observer effect reminds us that we cannot detach ourselves from the systems we measure. Our instruments, our choices, and our presence alter outcome. Yet this need not imply that the universe is conjured by consciousness alone. Instead, it may suggest that reality is relational foundational that what we experience is a product of interaction between observer and observed, a dialogue rather than a monologue. In the end, the question, do we create reality, may remain unanswerable, suspended between science and philosophy, but its power lies in the tension it evokes, forcing us to reconsider our place in the cosmos. Are we passive witnesses or active participants? Do universal laws dictate all outcomes, or does human agency weave itself into the fabric of existence? The mystery endures, as unsettling as it is profound, inviting us to live with the possibility that reality may not be fully real until it is shared. Quantum consciousness, could the mysteries of the mind be rooted in the mysteries of the quantum world? Consciousness remains one of science's most enduring enigmas. How do electrical signals in the brain give rise to subjective experience, to thought, emotion, and awareness? Some researchers believe the answer lies not in the well-mapped circuits of neurons, but in the strained, delicate processes of the quantum realm. This possibility, known as quantum consciousness, stands at the border of mainstream skepticism and radical speculation. The conventional view is pragmatic. Neuroscience has made extraordinary progress explaining cognition in classical terms: neurons firing, synapses strengthening, brain regions communicating in vast networks. To most researchers, invoking quantum mechanics is unnecessary and extravagant. The brain, they argue, is too warm, too wet, too noisy for fragile quantum states to persist. Decoherence, the rapid loss of quantum effect in macroscopic environment, would dissolve delicate superpositions long before they could influence thought. In this view, consciousness, while still mysterious, is best explained through biology, chemistry, and information theory. Yet others are not convinced. The classical picture, they argue, still fails to explain the essence of experience, the hard problem of consciousness. Why should computation give rise to qualia, the vivid textures of inner life? Here, quantum theories step in, offering frameworks that extend beyond ordinary neural activity. The most famous proposal is the orchestrated objective reduction, OR model, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that microtubule structural components within neurons might host quantum processes capable of influencing brain function. In this model, consciousness arises not merely from computation, but from orchestrated quantum events woven into the brain's fabric. Though controversial, such theories captivate the imagination. If true, they imply that consciousness is not an accidental byproduct of classical chemistry, but a fundamental phenomenon tied to the deep structure of reality. Awareness could be a window into the quantum domain, a place where subjective experience and the fabric of the cosmos intertwine. Some even speculate that consciousness might be non-local, entangled across brains or extending beyond physical boundary. In this vision, the mind is not confined within the skull, but participates in the wider quantum field of the universe. Mainstream rejection remains firm. Experiments designed to test quantum effects in biology have yielded mixed results, and critics point out that extraordinary claims demand extraordinary evidence. For now, the idea that consciousness has quantum origins remains unproven, hovering on the edge of scientific credibility. Yet, history reminds us that today's heresy can become tomorrow's paradigm. Regardless of its scientific status, the notion of quantum consciousness carries profound philosophical weight. It reframes the question of what it means to be human. If awareness is rooted in quantum mechanics, then our minds are not isolated accidents, but expressions of the universe's most fundamental process. Consciousness becomes not an anomaly within matter, but one of its deepest properties, as integral as energy or motion. Such a view resonates with spiritual traditions that see awareness as woven into the cosmos itself. Even if quantum theories ultimately falter, their speculative potential remains valuable. They force science to confront the limits of current explanations and inspire new experiments probing the boundaries of biology and physics. They remind us that the mind is not easily reduced to circuits, that subjective experience continues to elude complete mechanistic description. In the end, the debate over quantum consciousness reflects the broader tension between skepticism and wonder. The cautious scientist insists on evidence. The dreamer dares to imagine connections between mind, and cosmos. Between them lies the possibility that consciousness is not merely a puzzle to be solved, but a mystery to be lived. Whether quantum mechanics plays a role or not, the exploration itself keeps alive the spirit of inquiry that drives both science and philosophy forward. Meaning in a quantum cosmos. What does it mean to live in a universe where certainty dissolves into probability? For some, the quantum cosmos whispers nihilism. If events unfold not through intention but through chance, then perhaps existence itself is meaningless and accidental fluctuation, no more significant than dust swirling in sunlight. From this perspective, randomness feels cold, stripping purpose from human life. We are not chosen, only coincidental, drifting in a universe that cares nothing. Yet this interpretation, while stark, is not the only one. To call the quantum a realm meaningless to impose a human hunger for order onto a reality that is richer than we imagine. Randomness is not chaos, but possibility. Probabilistic laws do not erase meaning, expand it. For within uncertainty lies the capacity for novelty, creation, and emergence. Without unpredictability, no star would form, no life would evolve, no thought would diverge from repetition. What looks like disorder is, in truth, the engine of becoming. Entanglement further unsettles nihilism. If particles remain linked across vast distances, then separateness itself is illusion. We are not fragments drift, but thread in a woven tapestry. Randomness may shape outcomes, but interconnectedness gives them coherence. The cosmos is not empty machinery, but a dynamic web where events ripple outward, touching the whole. In this light, meaning arises not from predetermined design, but from participation in an ever-expanding symphony. Philosophers often debate whether meaning is discovered or created. The quantum perspective suggests a third path. Meaning emerges through relationship. Just as a particle's state takes form through interaction, so too does human significance crystallize through connection with others, with the world, with the unfolding universe. Randomness ensures unpredictability, but interconnectedness ensures resonance. Together they form a cosmos, not devoid of meaning, but alive. To embrace this view requires shifting from control to one. In a deterministic universe, meaning might lie in deciphering fixed plan. In a quantum universe, meaning lies in the awe of participation. Every choice, every thought, every act echo through an entangled web we cannot fully grasp. We are not authors of a closed script, but co-creators in an improvisation that stretches from atoms to galaxies. This reframing transforms randomness from threat into gift. If life were predetermined, novelty would vanish. But because the cosmos is open-ended, creativity and freedom thrive. The uncertainty of quantum mechanics mirrors the uncertainty of human existence. Our futures are not fixed, yet neither are they void. They are possibility awaiting realization. In that tension, meaning is not handed down but born again and again in the act of living. Thus, the quantum cosmos invites us to stand at the crossroads of humility and wonder. We are neither the center of the universe nor irrelevant accident. We are participants in a reality that balances chance with connection, unpredictability with coherence. To call this meaningless is to overlook its grandeur. To see it as interwoven possibility is to recognize that meaning is not a static truth, but an unfolding relationship between self and cosmos. As we conclude this exploration, the question of meaning becomes less about cosmic verdict and more about human response. In a universe alive with randomness and entanglement, will we despair at uncertainty or marvel at the chance to be part toward a new understanding of reality? Human beings are wired to crave certainty. From childhood, we learn to predict outcome. Drop a ball and it fall, touch fire and it burn. These experiences shape an intuition rooted in classical cause and effect logic, where order and determinism provide stability in an otherwise unpredictable world. Certainty comforts. It gives structure to decisions, confidence to act, and meaning to memory. Without it, survival itself would feel impossible. Our ancestors did not ponder probabilities, they relied on instinct. that assumed consistent rule. Quantum mechanics, however, dismantles this deeply ingrained expectation. At the subatomic scale, particles refuse to conform to deterministic simplicity. An electron exists in a haze of probability, occupying many potential states until measured. Photon behaves like a wave until it suddenly acts like a particle. Outcomes are not determined in advance but emerge from probability, collapsing into reality only when forced by interaction. Where human intuition demands clarity, quantum reality insists on ambiguity. This clash unsettles because it undermines the very tools our minds evolved to trust. We imagine cause leading directly to effect, but quantum theory whispers of chance and indeterminacy woven into the fabric of existence. Einstein's resistance, his refusal to believe that God played dice, echoes this discomfort. To him, randomness signaled incomplete failure to uncover hidden laws. For Bohr and his contemporaries, however, indeterminacy was not failure but feature, a truth revealed by experiment no matter how paradoxical. Consider the role of probability in daily life. We use it cautiously as an approximation of uncertainty, rolling dice, forecasting weather, predicting election. But in quantum mechanics, probability is not ignorance of deeper order, it is reality itself. The universe does not merely seem uncertain, it is uncertain at its core. This distinction challenges intuition because it denies the existence of hidden certainty waiting to be discovered. Our minds resist this lesson because they evolved on a scale probabilities average out. Billions of particles act together to create objects that appear solid and predictable. Entropy increases consistently enough to make time feel like a one-way arrow. Cause and effect dominate our macroscopic life. Only by diving into the quantum realm does the illusion crack, revealing a truth alien to our instinct. The certainty we trust is emergent, not fundamental, a collective effect born from statistical regularity. This raises philosophical tension. If the universe is fundamentally indeterminate, what does that mean for meaning, choice, or causality? Does randomness erode the sense of purpose, or does it instead invite freedom, suggesting that not all is preordained, that chance itself is part of creation? Quantum indeterminacy unsettles, but it also expands possibility. It suggests a universe less like a rigid machine and more like an unfolding story, improvising as it goes. Yet even as intuition failed, imagination adapts. Science fiction embraces the quantum strangeness of parallel worlds, time travel, and probability-driven futures. Artists and philosophers draw inspiration from uncertainty, seeing in it a metaphor for human freedom, creativity, and the unpredictability of life itself. What feels unsettling in physics becomes liberating in art. Indeterminacy, once resisted, becomes a canvas for new ways of thinking about existence. Still, the contrast remains. Human intuition seeks closure, but quantum mechanics withholds it. The mind longs for definitive answers, but reality offers only probability. Perhaps the greatest challenge is learning to live with this dissonance, embracing uncertainty, not as a flaw, but as a fundamental feature of the cosmos. Certainty comforts us, but uncertainty drives curiosity, compelling us to explore. In this light, the conflict between human intuition and quantum reality is not a dead end, but a doorway. It invites us to transcend instinct, to cultivate new ways of understanding that reach beyond survival-based logic. The universe may be indeterminate, but our capacity to find meaning within its ambiguity is limitless. Bridging science and philosophy, quantum mechanics has always unsettled the boundaries of knowledge. It is not merely a body of equations predicting particle behavior. It is a challenge to how we think about reality itself. Science, built upon measurement, evidence, and repeatability, suddenly found itself speaking in terms of uncertainty, probability, and paradox. Philosophy, long concerned with meaning, existence, and truth, discovered its abstract questions mirrored in laboratory experiment. The two disciplines, once diverging paths, now seem compelled to converge. Consider the problem of measurement. Empirically, quantum theory worked flawlessly, powering technologies from semiconductors to MRI machines. Yet philosophically, it provokes discomfort. What does it mean that a system exists in superposition superposition until observed. Does observation create reality or merely reveal it? Science provides predictive power, but philosophy probes the deeper significance, asking what reality truly is when nature itself refuses to offer a definitive picture. Historically, science prided itself on leaving metaphysics behind. The triumph of Newtonian mechanics seemed to show that nature could be described without appeals to mystery, but quantum mechanics resurrected questions once thought banished. Does causality always hold? Is time fundamental or emergent? Are human minds participants in the universe's unfolding or mere spectators? Empirical rigor alone cannot silence these questions, for they emerge directly from the interpretation of experimental results. Einstein himself wrestled with this bridge. Though he helped launch quantum theory, he recoiled from its philosophical implication. God does not play dice, he protested, clinging to determinism. Bohr, in contrast, insisted that physics must accept what nature shows, however counterintuitive. Their debates were not just technical disputes, but philosophical duels, wrestling over whether reality is rationally ordered or inherently probabilistic. These dialogues demonstrate that science and philosophy cannot be fully disentangled when the nature of reality itself is at stake. Today, the conversation continues. Quantum entanglement challenges locality, suggesting the universe is deeply interconnected. Philosophically, this resonates with ancient ideas of unity and interdependence, yet the evidence comes not from speculation, but from experiments violating Bell's inequalities. Likewise, quantum cosmology confronts questions of origin. Was the universe born from randomness, necessity, or something beyond comprehension? Such questions echo through both physics conferences and philosophical treatises, demanding collaboration rather than separation. This bridging also reshapes existential reflection. If the universe is probabilistic, does human freedom acquire new grounding? If consciousness plays any role in measurement, however slight, does it elevate subjective experience from biological accident to cosmic participant? Even if such interpretation remains speculative, they fuel inquiry into the meaning of existence in a quantum world. Science gives us data. Philosophy turns that data into orientation, challenging us to ask not only how the universe works, but what it implies for our place within it. Crucially, bridging science and philosophy does not mean abandoning rigor. On the contrary, it means recognizing that rigor itself must be complemented by reflection. Philosophy without science risks drifting into unfalsifiable abstraction. Science without philosophy risks blind application without understanding. Together, they offer a fuller picture, one rooted in evidence yet alive with meaning. Quantum mechanics, in its strangeness, demands this partnership more than any other scientific revolution. In bridging the two, we also touch on culture, art, and human identity. Quantum ideas have inspired literature, film, even spirituality. Popular fascination with parallel worlds, time loops, and entanglement demonstrates that quantum theory is more than physics. It is a language for reimagining existence. This cultural resonance testifies to its philosophical weight. People sense that in quantum mechanics, science is brushing against truths too vast to be contained within laboratories alone. Thus, the discoveries of quantum mechanics do not simply extend scientific knowledge, they redefine the very act of knowing. They force us to admit that logic, mathematics, and experiment meet mystery, paradox, and wonder. To reconcile them is not to diminish either science or philosophy, but to let them enrich one another. In that reconciliation lies the possibility of wisdom, an understanding both precise and profound, empirical and existential, practical and poetic. A future shaped by the quantum realm. Every era imagines its future through the lens of its dominant science. For ancient civilizations, destiny was inscribed in the heavens, dictated by constellation gods. For the industrial age, the future was a machine, predictable, mechanical, and built by human hand. Now, as the quantum realm reshapes our understanding, the horizon no longer resembles a clockwork mechanism or divine script. It resembles a tapestry woven of probabilities, entanglements, and emergent possibilities. Humanity's fate will not be written in stone, but co-authored through courage, imagination, and the tools quantum science places in our hand. Quantum technologies stand at the forefront of this transformation. Quantum computers promise more than speed. They promise access to realms of complexity previously permanently sealed. Simulating molecules may yield cures for diseases, breakthroughs in sustainable energy, and architectures for artificial intelligence beyond current comprehension. The future shaped by these machines will be defined not only by problem-solving but by creativity, as quantum algorithms uncover solutions alien to classical reasoning. To harness such power requires humility, for these systems may guide us to territories we cannot fully predict, yet must responsibly navigate. Quantum communication carries parallel potential. Entanglement-based nets could create an internet, immune to eavesdropping, reshaping global trust and diplomacy. Imagine a society where information flows with absolute security, where transparency and accountability are enforced not by law, but by physics itself. Such a shift could recalibrate geopolitics, economics, even personal privacy. Whether this creates liberation or new hierarchies depends on how wisely humanity distributes such power. Beyond technology lies cosmology, and here the quantum lens reveals an even more profound future. The inflationary multiverse and quantum branching suggest we inhabit not a singular cosmos, but a vast infinity of universe. If true, our destiny is no longer confined to survival within one fragile world. Instead, humanity becomes part of an infinite story, one in which every choice reverberates across countless variations. Such a realization humbles and empowers simultaneously. Humble because our universe is but one bubble among countless others. Empowers because the act of choosing becomes an existential gesture that shapes not only this world, but innumerable parallel ones. Yet perhaps the greatest transformation is not technological or cosmological, but philosophical. Quantum mechanics demands existential courage. It tells us that certainty is an illusion, that control is partial, that we are inseparably woven into a reality we cannot fully master. For some, this inspires dread. How can we chart a future if the ground beneath us is probabilistic? But courage lies in embracing uncertainty not as void, but as possibility. A future shaped by the quantum realm is not predetermined. It is open, demanding creativity, responsibility, and awe. This courage must extend to how we define intelligence and identity. As quantum-powered AI emerges, we may discover that intelligence is not a linear race, but a partnership across different modes of thought. Machines may navigate probability in ways beyond human capacity, while humans contribute imagination, values, and meaning. The fusion could redefine what it means to be conscious, blurring the line between biological and artificial, personal and collective. Our future selves may not resemble us in form, but in essence, beings shaped by curiosity, interconnectedness, and the courage to explore the unknown. The quantum future also compels us to reconsider destiny itself. If time can bend, if universes can branch, then destiny is neither rigid nor absent, it is relational. We are not passive travelers on a fixed path, nor solitary wanderers in chaos. We are participants in a grand improvisation where each action ripples through the fabric of reality. Destiny in this sense is not something discovered, something made continuous by how we engage uncertainty and connection. Looking forward, one truth becomes clear. The quantum realm is not merely a chapter in science. It is a turning point in human self-understanding. It challenges us to grow beyond fear of randoms, beyond hunger for control, into beings capable of wonder and resilience. The future shaped by quantum reality will not be easy. It will be strained, disorienting, and full of paradox. Yet, it will also be rich with possibility, offering humanity the chance to become not just survivors of a cosmos, but conscious co-creators of its unfolding story. In that vision lies our greatest task, to step into uncertainty with courage, to embrace infinity with humility, and to shape a future worthy of the quantum cosmos that birthed us.